Then we need to transform the result to the time domain. Okay? So mathematically, you need to perform inverse Fourier transform. Okay? We have big AC, which is like this. What would be the corresponding inverse Fourier transform? Maybe you are familiar with the Fourier transform of different functions. But here, you are facing Fourier transform or inverse transform of equation, not just function, right? 这边要做的转换是对方程式做转换，不是对函数转换而已， right? You know the square function, Fourier transform is a sinc function. It's the transform of functions. Here, this is not a function. This is a equation, right? How to operate the transform. 结果会是什么? The first one is quite easy. Big AC after inverse transform is a small AC of t. That's a matter of symbol. Okay. But how about this? 1 minus LC plus G, they are just constant, so no problem. But here, you have a constant, complex constant, times omega squared. Okay, this is something you need to transform. Because the variable in the frequency domain is omega. This is not constant. This is a variable. So after inverse transform, you should not see any omega. You should see t, right? Time domain variable t. But how to perform it? How to perform inverse transform for this one? 其实不是针对它啦，是这个乘这个一起做，这个乘积来做 inverse transform. What is the corresponding inverse transform? Good. You have minus omega squared, right? It can be decomposed into the product of j omega times j omega. And for each j omega, what is the corresponding time domain description? Time derivative, first order time derivative. So you got second order time derivative in the time domain. Okay, so that's why you have this. Minus omega squared is replaced by second order time derivative. Of course, big A of omega is replaced by small a of t. It's a matter of symbol. And that is the picture. What have we done? The initial condition here, we have done all this. We got big AC as shown in the previous slide. And in this slide, we perform inverse transform here. Okay, we have been here. But there are other things to be carried out, so to be analyzed later. The reason we need to perform inverse transform is quite easy. The following three effects had better be analyzed in the time domain. So we perform inverse transform, bringing our function from frequency domain, big AC, to time domain, small AC. Then we can do the analysis in the time domain. Okay. How about the curves? Okay. If you observe the blue curve here and here, what's the difference? This is input pulse in time domain. Blue curve means intensity. Okay. The difference between this intensity and the AC intensity is AC is broader and shorter. 高度变小，然后宽度变宽。Why? Why the peak is lower? Because of cavity. You have linear loss. Okay, you have to lose some energy. Why the pulse duration is broader? Which one? GDD plus spectral filtering. Spectral filtering means you have to sacrifice some bandwidth. It also means you have to be with a broader pulse duration. Okay, so they are they make sense. OK， 我不是乱画的，是 based on 这个实际上的发生的情形。Then, in the time domain, first we deal with the effects of two things: satural absorber and the dynamic gain. Okay. They are better modeled in the time domain. So we have intensity and the time-dependent loss. L is not a constant but a function of time. Okay. If you look at this symbol, it's time-dependent. But in reality, it's not just time-dependent, but also intensity-dependent. The physical mechanism is satural absorber, right? 我们在 lesson 3有讨论到我的 loss in the presence of optical pulse. Your optical pulse is not a constant; it's a function of time, right? In the presence of optical pulse, your loss curve will change because of the pulse. Okay. So in principle, it's intensity-dependent loss. But since your pulse is a function of time, so in the end, it's a function of time. And again, you have the similar thing, intensity and the time-dependent gain. G is no longer a constant, but a function of time, G of t. Okay? So actually, we separate the contributions of gain medium into two different parts, right? In frequency domain, it's represented by the spectral filtering effect because you have finite gain bandwidth. But in the time domain, it's here, dynamic gain, the saturation of the gain curve in the presence of your optical pulse. So physically, you have a single piece of gain medium. But mathematically, the contributions are dealt with in two different places. Okay, filtering effect in the frequency domain, dynamic gain effect in the time domain. OK， 所以其实我们操作了这个数学模型啊，虽然物理上它就是一个 piece of gain medium， 但是数学分析上我把它放在不同的地方处理。Okay, and if we assume the dynamic loss is pretty weak, L of t is always much less than 1, then the output pulse A4 of t is equal to e to the minus LT times the input small a3 of t. But G has to be generalized to function of time. And the e to the minus LT is close to 1 minus LT because of the assumption, weak dynamic loss saturation. And the A3 of t is replaced by the result in the previous slide. And using the same the rule, only the lowest order terms are preserved. You got this. This is a function, this is an equation in the time domain. Okay, not finished yet because we have something else to deal with. The SPM effect. Okay. Here we assume the maximum nonlinear phase shift is still weak. Delta phi max equals some parameter delta times the peak power. And even the maximum nonlinear phase shift is still much less than pi. This is our assumption. Okay. And what is delta? Delta is here. It's very easy. Phase shift is delta k times working distance L, right? 我漏掉了一个 L。那你把那个你的 change of wave vector delta k is equal to change of refractive index times wave number in vacuum, right? And the change of refractive index is N2 times I. I is replaced by peak intensity. That's why you have a peak power term here. Grouping all the other terms together, you got the SPM coefficient delta. Okay. 我这边应该是少了一个 working distance L. Okay. Then the following things are the same as before. output A5 equals input A4 times SPM e to the minus j delta times P of t. Okay? The phase modulation in the time domain changes with your optical pulse shape P of t. Okay? Then everything else should be very straightforward. 我就不再重复. Basically, you can arrive at a new time domain equation. We are very close to the end. Yes.
How do such approximation?
Which one?
Delta phi max is smaller than.
Okay. Let's see in this way. First, you assume it. You got some easy solution. Then you have to examine whether your experiment is by this assumption. If it's not the case, it simply means the easy solution does not apply. You have to work in a more tedious way to get the solution, maybe numerical simulation. But without doing so, that means you cannot have this equation, and also means you cannot have analytic solution. Okay. 那倒过来讲，就是这个条件会不会被违反？常常会被违反。你很容易在目前商用的雷射发现你的工作条件，这个是没办法成立的。那也就代表我最后找出来的 solution，second hyperbolic solution does not apply。也就是你买来的雷射，你真的去量它的 pulse， 它不是 second hyperbolic function， 常常会违反。But 我想重要性在于它给你一个解析解，把所有的概念都包含在里面。那当然，这个模型无法给你一个精确的预测你实验上遇到的 laser 是不是刚好就这样，大概很难。但如果连这些都没有，你就无从去了解 basic 的 working principles. The purpose of this model is simply introducing what are the basic working principles of pessimal locking. That's it. Okay. Any other question? No? Okay, so maybe let's stop here.